one more example of long division of polynomials. A little more complicated than before, but trying to be pretty simple, really. We've got a cubic still as the dividend. Now the divisor is a quadratic. The degree of the divisor is still less than or equal to the degree of the dividend. Otherwise, we would be done. We wouldn't be able to divide. And to start the process, we just look at the leading terms. 3x cubed divided by x squared. That just gives us a 3x. Then we multiply the current quotient by the divisor. We're going to get 3x squared plus 6x minus 9. If you want to write that kind of thing out as a sidebar calculation, really not a bad idea. Oh, 9x, my bad. I'm talking and not thinking. 3x squared minus 9x. Okay, so that was something where I was not being careful. 3x times x squared, 3x cubed. Goodness, really not being careful. 3x times 2x, 6x squared, and 3x times minus 3, minus 9x. So because I was talking and not thinking, I just so the x kind of slipped under the radar. I think that's a fairly common mistake as well. Okay, now I've done that part. I've multiplied this by all of this stuff. I got 3 terms. Now I'm going to subtract. The 3x cubes cancel as they must. That's why we did that little division at the start. Now remember, I'm subtracting this whole thing. So you can think of it as like a minus and put parentheses around it if you want to really emphasize that. And that minus sign is distributing everywhere. So we're taking 2x squared and we're subtracting the 6x. That kind of screwed up my columns though, so I'm going to take it away. So 2x squared minus 6x is minus 4x squared. That's better. Plus 5x minus 9x plus 14x. And here's something I slipped up on the first time I recorded this. I didn't bring the minus 6 down. That's an easy thing to forget, right? You're taking this entire polynomial and you're subtracting this entire polynomial, which is essentially the part that you have successfully matched, and you're comparing them and seeing what's left over. And you don't want to forget to bring down everything, even if it doesn't kind of have a match here. It's the minus 6 is just, you're subtracting 0 from it, basically. Okay, so now we restart. We're going to say, how many times does x squared go into minus 4x squared? Well, that's just a number, which is indicating that we're almost done. When these degrees become equal, you're getting to the last step. It's your last true division step. So that's going to be a minus 4. All right, now I multiply it. Minus 4x squared. Let me make them line up a little better. And then minus 4 times 2x is minus 8x. That'll look a little better. And then minus 4 times minus 3 is plus 12. Okay. Now I subtract. Minus 4x minus a minus 4x squared will cancel. 14x minus a minus 8x gives us 22x. And minus 6 minus 12 is minus 18. Very easy to get signs wrong here. So you got to be slow and careful. What is this? Well, because this has a degree, the degree of this is 1, is less than this guy, there is no possible further division. We have got the remainder. So the remainder is itself usually a polynomial. It's a polynomial whose degree is guaranteed to be less than that of the divisor. But other than that, it's not guaranteed to be any simpler. So here, if we have the one form of summarizing what we've discovered, we would say when we divide 3x cubed plus 2x squared plus 5x minus 6, and we divide that by x squared plus 2x minus 3, we get a quotient of 3x minus 4. And then what's left over is a simpler numerator, but over the same exact denominator. All right. So this is kind of like the mixed number thing I was showing in the other video on the right-hand side. And this is the original quotient we're trying to simplify. This might not look like incredible progress, but it has split out on one part that's just a polynomial. That's a lot simpler than one of these guys. And we'll take a little look at how complicated the graphs of these guys can get, for example. And it has simplified the numerator. It's still a quotient. It still has the same denominator, but at least it's what analogous to what you'd call a proper fraction for numbers. The degree of this numerator is smaller than the degree of the denominator. If you want the other summary that doesn't even mention division explicitly, you can always turn a fact about division into a fact about multiplication. It says that if I try to reconstruct the original polynomial I was interested in, I can come fairly close by taking my desired divisor, 3x minus 4, or sorry, my divisor was x squared plus 2x minus 3, and multiplying it by this quotient that I found with this process, but I'm not going to get it exactly. I have to add this annoying remainder. Okay, so it's good to know that these are the two forms, just sort of pure algebraic statements that summarize what we've accomplished using this very particular kind of way of writing the process of long division. So let me show you something that's rather slick. I'm going to go back to this example. Let me steal this example again. And this was of a very particular form. This was, oh, that was some scratch paper. Okay. And that was where I divided a polynomial by just x minus k, x minus a number. So the leading coefficient was 1, and it's just a linear polynomial. And I'm very particularly going to think of it as dividing by x minus k, because that has, it's nice to think of it in terms of x minus instead of x plus. And we'll see one of the many reasons for that in a second. And the idea is that there's writing all the x's and stuff, there's a lot of redundancy here. And if you look at what happened, calculation, there's really not much that happened. The 2 just kind of dropped down and actually just showed up here unchanged. The degree, the x cubed turned into an x squared, but that's kind of very predictable. That's not going to be different in any examples. Whatever this degree is, you divide it by an x, it's just going to kill off. It's going to cancel out one of the x's. So that wasn't very complicated. And then what was the crucial thing here? That minus 8 was the 2 times the minus 4. And then I subtracted the minus 8 from the minus 3. What was the upshot of that? I'm doing a minus 3 minus the minus 4 times the 2. And whenever you do this step, it's always going to be that minus a minus. That's a silly way to write that. Why don't we just do it as minus 3 plus 4 times 2? Oops, sorry, you needed equals there. Okay. That's going to be where that 5 comes from. Then what happened to the 5x squared? It just turned into a 5x. The 5 didn't change because all I did was I divided by x. And then what did I do? That minus 20 came from a 5 times a minus 4. But wait, I'm subtracting that. Turns out I actually ended up just adding a 20 to the existing minus 10. Okay, so went through that really quickly because the book has a pretty nice slower description of that. Let me show you this really slick tableau. This is called synthetic division. It only applies, I think I have that just up here. Yeah, we can use only, I should really emphasize, only when the divisor can be written as x minus k. And so that again can be confusing. It's like the sort of x minus h kind of thing in vertex form. It's very related to that. If we're going to replicate this calculation, and we know we're dividing by x minus 4, it's a little confusing, but we're just going to put a 4 there. And we know that represents the fact that we're dividing by x minus 4. If this was x plus 8, we would actually put a minus 8 in this little slot. I'm sorry about that. Okay, so I'm just taking away all the x's. Why it's called synthetic is it's like really stripping it down. Very efficient, but it's a little cryptic because somebody who didn't know what we're doing wouldn't have any idea that this is actually secretly dividing polynomials. But let me illustrate the steps, and we'll see that it exactly matches this, but with some simplifications. First step is all we do is we just drop that leading term down. Just literally rewrite it. And then we just do 2 things repeatedly. It's really nice. We multiply that 2 times the 4, and we put it in this slot here. Ooh, I don't want to do that. Let's kind of go in. Okay, I fixed my little typographic problem. So the key step is we're going to multiply the 2 by 4, and we're going to get an 8. And then remember, that was written as a -8 here, and we subtracted it. So we're being clever. Because we changed this to a 4 and not a -4, we have to do a simpler operation. We take the 2 times the 4 to get an 8, and then we add these guys. So you multiply, so multiply this one number by the number here, put it here, and then you add to the top row. And so that's going to be, whoa, hello. Totally in the wrong place. And so we're going to add that in, and we're going to get the 5, right? So that replicates this 5 right up here. Sorry, my mouse pad is, or my trackpad is getting really crappy. Okay, now what do? We take the 5 times the 4. We get a plus 20 here. That's instead of the minus 20 here. And because we flip the sign, we don't subtract, we add. Minus 10 plus 20, and that's 10. So notice one thing, that one of the easiest things to get wrong here is the fact that we write this, but then we subtract it, and it's very easy to get the signs wrong. This is really simpler, because as long as you know, you can practice a little bit, you just multiply, like the 5 times the 4, and add. There's fewer subtractions, fewer minus signs, less opportunity for error. Now, 10 times 4 is 40, and I add that, and I get 33. Now, what does this mean? It's interesting how it shows up. This was symbolizing the coefficients of a cubic, and then this guy, actually, this row has everything in it, but in a little bit of a weird way. Everything but the last number is the coefficients of a quadratic, and so you have to know that that's kind of the symbolism. So it says the quotient here, as we saw above, the quotient is 2x squared plus 5x plus 10. That's what this part is saying. And the remainder automatically shows up as the last number in that row. Remainder is 33. Because it was dividing by x minus k, a linear polynomial, the remainder really is just a number. Usually, as I saw in the previous example in this video, the remainder can be a polynomial. But when you divide by a linear function, x plus or minus a number, the remainder has to have degree less than that. And the only kind of polynomial that has degree 0 is just a straight up number. So it's a little bit weird that you've got this one row that combines two kinds of information: the coefficients of the quotient and the single number at the last, which is the remainder. Okay, we'll do more examples in class, and you can also look in the book, but I wanted to introduce that.